Hello, in this video I'm going to show you how to answer an exam question on finding enthalpy change experimentally and then using a Hess cycle. So this question is from the year 2010 and it's from a 322 paper and it's question 3. It starts off giving an equation for glucose being completely combusted. So if you notice, this is the standard enthalpy change of combustion because there's 1 mole and everything's in the standard state. They give you some extra information, but simply put, they want to know what the oxidation process is known as in the body, and that is, of course, respiration. So, moving on to the actual experimental process. A student carries out an experiment to determine the standard enthalpy change of combustion of glucose, and they have quite a lot of numbers, and the best thing you can do for these questions is go through and just like highlight everything and be aware of what you've got. So you've got a mass of glucose burned, okay, so that's going to be a mass somewhere. We've got 100 cubic centimeters of water, that's a volume obviously, and then we have this temperature change here. And you have to calculate the energy released in kilojoules during combustion of 0.831 grams of glucose. So this is that mass of glucose. Energy released, you're going to use the equation Q equals mc delta T. They give you these two bits of information. The density of water, 1 gram per centimeter cubed, tells you that this volume, 100 centimeters cubed, is also equal to 100 grams. So the first thing we do is put in 100. C is the specific heat capacity. They're giving us 4.18. And then over here, we have got the two temperatures, the initial and the final. So to get the temperature change, you're going to do 41.0 minus 23.7, and that equals 17.3. So there, we're going to put that into our equation as delta T, put these all together, and you get 7,231 joules. You're asked for it in kilojoules, so divide by 1,000, 7.23 or 7.231 is going to be fine. Okay, in fact, it was 7,231.4. Right, so that's your 2 marks. 1 mark is for just knowing Q equals mc delta T, and then the second mark is for converting it to kilojoules after doing the correct sum. Now, you didn't use this mass here, and this is the one that is the most common mistake. Q equals mc delta T. The M is the mass of what it is that you're heating, so it's the amount of water most commonly. The 0.831 grams is almost like a decoy there. You're going to need that later on. And what sometimes is a good idea is to look all the way through the rest of the question before you jump into the first one. It reduces the chance that you use the wrong mass here. The second part of the question wants you to get the amount in moles of glucose that's burned. Well, number of moles, if it's the only information we've got about glucose is the mass, so you have to use sample mass over molar mass. First thing we'll have to do is calculate that molar mass. Glucose, we're given C6H12O6, so 6 times 12 for carbon, 12 times 1 for hydrogen, 6 times 16 for oxygen, gives us some good darts, that's 180. We'll take our mass up here, 0.831, divide it by the 180, and that gives us 4.62 times 10 to the minus 3 moles. 1 mark for 180 and 1 mark for doing this. You could get error carried forward if you'd used the wrong 180. Right. The final part here is where we've got to calculate the enthalpy change of combustion of glucose. That means we need to know what it is, the energy change is for 1 mole. So you're going to basically look at ratios. You had 4.62 times 10 to the minus 3 moles, releasing 7.23 kilojoules. So you want to find out what 1 mole releases. And the easiest way to do that would be to take your original amount of energy and divide it by the number of moles that gave that. And what you should get here is, oh hang on, we want 3 significant figures. So we're going to get 1,560. Now this is going to give us 1 mark. There's a crucial thing that we need to be aware of. this was an exothermic reaction. It was energy released. So we need the sign to be in there. So there was 1 mark for having the minus sign. And even if you got this all correct, if you didn't do the 3 significant figures, you wouldn't have got the very first mark. Okay, over the page. This is the same chemical, it's the same equation, but they're showing that you can also determine it indirectly, as in you can use a Hess cycle. So we are given standard enthalpy change of formation for each of the 3 chemicals, glucose, carbon dioxide and water. Well, we've got carbon dioxide, water and glucose. So we need to make a triangle here, and because they're all the standard enthalpy change of formation, what we need down here are the elements in their standard states. So that's going to be 6 carbons as a solid, 6 H2 as a gas, and then careful, so 6 times 2, 12, and 6, 18, 9 O2 gas in total. And you want one arrow that goes from these elements up to the carbon dioxide and water, and then another for the reaction where you take the elements and you form glucose. Now, key thing, the standard enthalpy change of formation of an element is 0. So here you have 6 O2s basically doing nothing. There's no change, so we can not worry about them. When I get these triangles, I always look for the fact that there's one set of the chemicals have 2 arrows going away, and one set of the chemicals have 2 arrows coming in. The chemicals with the 2 arrows going away are like our ultimate reactants. These with the 2 arrows coming in are the ultimate products. And the final chemicals have an arrow going in and an arrow going out. So reactants and products, and these are the intermediates. The direct route I always call A, and then I call the other steps B and C, because then every single time I know it must be true that the direct route equals the sum of the indirect route. This change is equal to these 2 changes put together. So now you need to go through and figure out what energies are actually happening for each of A, B and C. So for route A, we are turning carbon and hydrogen and oxygen into carbon dioxide and water. So it's going to be using the enthalpy of formation of carbon dioxide and of water. So we're going to have the standard enthalpy change of carbon dioxide. It's meant to be a naught, my apologies, and the standard enthalpy change of water. But look, 6 carbon dioxides and 6 waters, so you must multiply these by 6. So what we've got is 6 times minus 394 plus 6 times minus 286. So that equals minus 2364 plus minus 1716. So overall, this is minus 4080. That's for A. What about B? We're taking the elements. Oxygen doesn't do anything, so this is just the standard enthalpy change of formation of glucose. And there's only one of those, so this is a very nice and easy mark, because simply put, it is minus 1250. Now what about C? This is the thing we're asked to find out, and we're therefore just going to have to rearrange this equation. There's no value given, we've got to determine it. If A equals B plus C, then C is A minus B. And it's important to draw the cycle out, and it's important to write these steps out, because this way you're not going to miss a minus sign. A is negative 4080, and then it's minus 1250. A lot of people will combine these two, but actually subtracting a negative becomes adding, and so the final answer here is minus 2830. Now, marks were given for realizing that you had minus 4080, one for this and one for getting the 1250, but they had it as a plus 1250 because the minus. So the mark scheme wasn't as clear there. This is, all of this will give you the 3 marks. Okay, now they change back to comparing these values to the experimental value. And it's two reasons why the experimentally determined ones are less exothermic than the calculated ones. This is experimentally by us as students and teachers in a school, as opposed to using the absolutely perfect equipment. And the one that you always want to go for this is heat loss, but specifically to the surroundings. You must specify that the energy that's being released by your combustion is then being lost out to the surroundings. That's the crucial part. Heat loss itself wouldn't get the marks. The next most common reason is incomplete combustion. So what happens here is the mass of your fuel is different to the amount you actually got energy out of. If you do these experiments and you look on the bottom of the vessel that contains the water, you will see soot. That is uncombusted carbon, which you could extract more energy from. So it means there's less energy, you haven't been as efficient, you haven't got everything out. So incomplete combustion. And then the final part is, there's 2 marks, they're the 2 to go for. It's always worth adding in the third and saying non-standard conditions, because of course everything that you're doing in the lab is not going to be perfectly at the standard conditions. Thank you.